All right, so this video is going to go over how we can find the different kinematics variables or motion variables from position graphs and from time graphs. So as a reminder, X represents position, that is where we are located, and that is a vector quantity. Delta X represents a change in position, also known as a displacement. And that can be found by doing the final position minus the initial. It's really important that we're doing final minus initial. That's also a vector. Okay? Then kind of the scalar sibling to change in position is distance. That's how far we've actually traveled. Like I said, that's a scalar. For velocities, we have instantaneous velocity. That's the rate of change of position at a specific instant in time. It's a vector, so we have magnitude and direction. We have average velocity. Okay. That is, again, another vector. We have two ways to calculate average velocity. We can do average velocity as our change in position over time. Or if we have constant acceleration, which we will for a lot of parts of our class, we can find the average velocity by doing the initial plus the final divided by 2, so finding the actual average. But again, that's only if we have constant acceleration over the time frame. Then we have A, which is our instantaneous acceleration, the rate of change of velocity. And then A average is our average acceleration, which is going to be the change in velocity over time, V final minus V initial. We also have speed and average speed. Speed is defined as the rate of change of distance. And we can find average speed by doing the change in distance over the change in time. All right, so first we have this position versus time graph, where we have, it looks like a couple of different sections of motion. So on this position versus time graph, let's say I wanted to find a specific position, right? I wanted to find where I am at 7 seconds. Because this is a position versus time graph, this graph tells me exactly where I am at specific points in time, or as time goes on. So all I need to do is figure out where 7 seconds is, which will be right here. And I need to follow until I get to when I hit the graph here. And I just need to read this y-axis value, which will be negative 25 meters. If I wanted to find, let's say, the position at 13 seconds, right, I would go and I would find 13 seconds, which is here, and I'm on the x-axis, so that means my position is 0 meters. So to find our positions at specific points in time, we're just reading off of the graph. Now let's say we might want to find our change in position. Our change in position is something that's going to occur over a time frame. Right, so a period of time. So let's say our change in position from 1 to 3 seconds. Change in position is the final position minus the initial position. So where I am at 3 seconds minus where I am at 0 seconds. At 3 seconds, I have a position of negative 15 meters. And at 0 seconds, I had a position of 20 meters. So I have a change in position of negative 35 meters. From 0 to 3 seconds. All right, so the next thing we have is instantaneous velocity, right? Our rate of change of position. Well, I know that for any graph, the slope represents the rate of change. So that means the slope on this graph is going to represent rate of change of position or velocity. So here, I need to find the slope at that time. So let's say I wanted to find the instantaneous velocity at 1 second. 1 second, right, is right here. And I see that that is on a line. So as long as I can find the slope of that line, I will have the instantaneous velocity. So I can write it as the velocity is change in y over change in x, which is the slope formula. So negative 15 minus the initial 20 from 3 seconds to 0 seconds. So negative 35 meters in 3 seconds. That is not going to be a great number, but that's okay. 35 divided by 3. It's going to give me 11.7 seconds. Or not seconds, whoops, meters per second. Let's say I wanted to find the instantaneous velocity at 9 seconds. 9 seconds is right here. So that's going to complicate things a little bit because that is on a curve. Okay? So we can't really find the slope of a curve, but what we can do is find the slope of the line tangent to that curve. So if a line is tangent to a curve or another line, it means it hits that curve once and only once. So I'd get a straight edge. And I'd draw a dashed line to represent my line tangent to that curve. Now I'm going to try to find the slope of that line. So I'm going to try to find nice points. I should have probably done a solid line. There we go. So I'm going to use this point here and that point there. So my velocity is going to equal change in y over change in x. Let's see, we go from negative 10 meters from negative 30 meters, and that's 12 seconds, and this first one is at 7 seconds. So negative 10 minus negative 30 is the same thing as negative 10 plus 30, or 20 meters in 5 seconds. So my velocity there is 4 meters per second. Now, likely I would not have you find the slope of a curve, right? I'm going to have you find the slope of lines, right? But I would expect you to know what the slope of this curve is doing, okay? So the slope of this curve is decreasing in value, whereas the slope here is increasing in value. And that's ignoring any negatives, because yes, technically we're going from negative slope to 0, that is increasing, but I'm gonna just pay attention to the negative, or ignore the negative, there we go, and just look at what my slope is doing. My slope is flattening out, so that suggests that I am slowing down, aka slope is decreasing in value. Here, my slope is getting steeper, right? Increasing in value, so must be speeding up. Now, the other thing I might ask you to find is the average velocity. For instance, I might ask you to find the average velocity from 0 to 9 seconds. Or not 9 seconds, I meant 8 seconds. There, that'll make it a little bit easier. So we know that the average velocity is change in position over time. And I can find the actual average between two velocities, but that doesn't really play a role in this type of graph. I'm really just going to look at change in position over time. So at 8 seconds, my position is negative 25, minus my position at 0 seconds, which is a positive 20. And that occurs in 8 seconds. So negative 45 over 8 is negative 5.6 meters per second. So what that means is, on average, between 0 and 8 seconds, I am traveling 5.6 meters in every second. That's what that number means, on average. Now, we could also find average acceleration from this graph, but we have to be very specific about where those accelerations are happening, because we only have 2 places where we're accelerating, this curve and this curve, because that is the only place where my slope is changing, my velocity is changing. So to find average acceleration, I know I need a change in velocity over a time. And I also need a time frame, right? So let's say from 3 to 5 seconds. So the velocity at 5 seconds minus the velocity at 3 seconds over the time. Okay. The velocity at 5 seconds, right just after 5 seconds, is 0 because my slope is 0. And the velocity at 3 seconds is the same as the velocity at 1 second, which I already calculated. So I'm going to call it 11.7 meters per second. Over a time of 2 seconds. Oh, wait, that was a negative 11. Oh, I got to go back here. This is supposed to be negative 11.7 meters per second. And this has to be minus a negative, okay. So 11.7 divided by 2 gives me an average acceleration of 5.85 meters per second squared. I could do the same thing from 8 to 10 seconds and find the average acceleration there. So average acceleration is change in velocity over time. The velocity at 5 seconds minus the velocity at 3 seconds. At 5 seconds, my slope is 0, so my velocity is 0. At 3 seconds, my slope is negative 11.7, so that's what my velocity is, and we divide by the time frame of 2. So that's pretty much the information we can get from position versus time. If we are velocity versus time, everything changes. So here we have a velocity versus time graph. Each of those highlighted sections means that there is a different slope value. Okay, so let's start with instantaneous velocity. Okay, so if I want the velocity at, let's say 4 seconds. Because this is a velocity versus time graph, that means this graph tells me the velocity at various instants in time. So if I want to find the velocity at 4 seconds, I just need to go to 4 seconds and go down until I hit the graph. My velocity at 4 seconds is going to be negative 15 meters per second. Okay, I can do the same thing at 11 seconds. I go to 11 seconds and I go up, and that's going to give me 5 meters per second. I could also find an average velocity. But remember, I can only find an average velocity if the acceleration is constant. Meaning, I couldn't find an average velocity between 5 and 10 seconds, because if I look, 5 to 10 seconds involves 1, 2, 3 different accelerations, right? Because I have 1, 2, 3 different slopes. So instead, we'd want to find the average velocity between, say, 4 and 7 seconds, right? We don't need to go all the way to the end of the interval. We can go 4 to 7 seconds. Okay? So to find the average velocity, I'm going to do first velocity plus second over 2. I'm finding the actual average. So my velocity at 4 seconds is negative 15. My velocity at 7 seconds is halfway between 2.5 and 5. So 7.75. Ooh, but that's negative. All over 2. So negative 15. 7.75. Oops, I forgot my negative again. And then divided by 2. So my average velocity in that time frame is negative 11.375. And let's do another example. Let's say it's the interval from 8 to 10 seconds. That's a nice easy one. Right, the average. Right, at 8 seconds, I have a velocity of 0. At 10 seconds, I have a velocity of 5. I am finding the literal average. So my average velocity there is 2.5 meters per second. So each of these different colored slopes would have different average velocities, and I could not do an average velocity using this equation for multiple colors. All right, another thing I might need to find is a change in velocity, right? Which is v final minus v initial, right? So that's from any time frame. So let's say, oh, I don't know, 0 seconds to 10 seconds. Right? So my final velocity at 10 seconds is a positive 5 meters per second. And I started at negative 15 meters per second. So my change in velocity is a positive 20 meters per second. Okay. So the next two things we're going to look at are instantaneous acceleration and average acceleration. Okay. Instantaneous acceleration is our acceleration at a specific point in time, or the rate of change of velocity at a specific point in time. And I know that the slope of any graph represents rate of change. So the slope of a velocity versus time graph represents rate of change of velocity, or the slope of the graph represents the acceleration. So if I wanted to find the acceleration at 1 second, I would need to find the slope of the line that time 1 second is on. So I would know velocity is change in y over change in x, right? My slope equation. So negative 5 minus negative 15, all in 2 seconds. I'm going from here to here. So negative 5 plus 15, that gives me 10 in 2. So, right, am I doing math correctly? Negative 15. Oh, I'm doing this wrong. No, I'm not. Negative 5 is the final. Minus negative 15 is the initial. My brain is not working today. Okay, that is 10 over 2. All right, so therefore we have a velocity at 1 second of 5 meters per second. That makes sense because I have a total change in velocity of 10 meters per second in 2 seconds. Okay, so again, to find instantaneous acceleration, you're just finding the slope of the line at any point. So if I wanted to find the instantaneous acceleration at 6 seconds, right, I could find the slope of this pink line. So change in y over change in x, it doesn't matter what part of the line you do the slope on. I usually go like start to finish. So 0 minus negative 15, and that is 8 minus 4. So 15 in 4 is a positive 3.75 meters per second. So that's our instantaneous acceleration. Then we have average acceleration. So this is good when we have time frames that cover multiple accelerations. So let's say I wanted to find the average acceleration between 0 and 9 seconds. Okay. That gets complicated because I have 1, 2, 3, 4 accelerations based on the 4 different slopes. But the other way that we can find the average acceleration is to do the change in velocity over the time frame. So v final minus v initial, well, at 9 seconds, right here, ooh, that's actually the 5th acceleration. So at 9 seconds, we are at 2.5 meters per second. And at 0 seconds, we were at a negative 15 meters per second. And that happens in 9 seconds. So this should be 17.5 over 9. And that gives me 1.94 meters per second squared. Ooh, I got all of my acceleration. Oh boy, sorry. These slopes over here were acceleration, not velocity. Silly me, which means my units need to be meter per second squared, not meters per second, because we were finding instantaneous acceleration. Let's got confused. So average acceleration, back to that. Change in velocity over time. So from 0 to 9 seconds, we had a positive change in velocity of 17.5 meters per second, 9 seconds. So we have an average acceleration of 1.94 meters per second squared. So that means on average for those 9 seconds, I moved or increased my velocity by 1.94 meters every second, meters per second every second. All right, now the last thing, that we can find with a velocity versus time graph. And this is the thing that can get a little bit tricky, okay? But that's going to be change in position. So there's two ways that we can find change in position. We can find change in position by using the idea that change in position is going to be equal to the average velocity times the time, or we can do the area between the graph and the axis. So some examples where it might be better to use change in velocity or change in position is average velocity times time. Let's say I wanted to find the change in position between 10 and 12 seconds. Well, between 10 and 12 seconds, that's right here, my average velocity is just 5 because that is what my constant velocity is. I'm doing that for 2 seconds, so I must have a change in position of 10 meters. Another example of when it might be nice to just use average velocity is, let's say I was going between 0 and 2 seconds. I wanted to know how far I moved. Well, between 0 and 2 seconds, I have an initial velocity of negative 15, a final velocity of negative 5. Negative 15 plus negative 5 is negative 20, and divide by 2. That means my average velocity is negative 10 meters per second. I do that for 2 seconds, so I travel negative 20 meters. Okay. So it's really easy to do when we have a section that is just constant acceleration, and we can use our v1 plus v2 over 2 equation for average velocity. So that's not too bad. Where things can get a little bit tricky is, let's say I wanted to figure out how far I traveled between 0 and 4 seconds. Well, between 0 and 4 seconds, I have 1, 2, 3 accelerations. So that means I need 1, 2, 3 average velocities moving at 1, 2, 3 different time frames. Okay? So I have 0 to 2, 2 to 3, and then 3 to 4, right? Based on how that graph is split up. Luckily, we already found 0 to 2, right? We know it is negative 20. From 2 to 3, I have a velocity of negative 5 and a velocity of negative 2.5. So negative 5 plus negative 2.5 divided by 2. My average velocity is negative 3.75 times 1 second, not S1. So negative 3.75 meters. And then from 3 to 4 seconds, right, I have a velocity of negative 2.5 and negative 15. So negative 15 plus negative 2.5 divided by 2 gives me an average velocity of negative 8.75 times 1 second. So negative 8.75 meters. And then I got to combine all of those, negative 20, negative 3.75, negative 8.75. And that gives me a grand total change in position of negative 32.5 meters. Another way to do this, another way of finding the change in position, I'm just going to erase some of these to clear things up. Another way to find change in position from a velocity versus time graph oh, excuse me, is to find the area between the graph and the axis. So let's use that example of 0 to 4 again. Okay. So here's 4 seconds. So I need to find the area of this weird shape here, right? All this purple. Now, it's not going to be in terms of boxes because I need to make sure to use the scale. So how do I find the area of that weird shape? Well, the answer is I don't, right? But what I can do is I can break that weird shape up into triangles and rectangles and squares. So I have 1, 2, 3, 4, 5 shapes. So area 1, that's a triangle, so 1/2, base times height, 1/2. That is a base of 2 seconds and a height of -10 meters per second. So that is an area of -10 meters. Area 2 is a square, base times height. And you could break these up however you feel like it, as long as you're finding right triangles and rectangles. So the base is 2 seconds, and the height is -5 meters per second, and I travel another -10 meters. Okay. Now this area 1 and 2 is also how we could find the change in position from 0 to 2 seconds. So if we added that up, -10 and -10, we got -20, which is the same answer we got when we used average velocity. So area 3 is a little baby triangle. 1/2 base times height, 1 second, times 2.5 meters per second, -2.5 meters per second. So that gives me -1.25 meters. Fourth area is a rectangle. So 2 seconds times 2.5 meters per second, negative. So that gives me -5 meters. And area 5 is a very skinny triangle with a base of 1 second and a height of, it looks like -10 meters per second. So that gives me an additional -5 meters. Right. Let's see. Oh, -10. Yes, -5. Okay, so when I add all of these up, 10, 20, 30, 1.25. Okay. -8.75. So I stopped the recording because I was trying to figure out why my answers were different. Why was this 31.25 and this was 32.5? And I figured out that I have been reading numbers wrong the whole time. I have been saying that these 2 points are at -15, and they are not at -15. -15 is down here. This is -12.5. So when I found my average velocity from 3 to 4 seconds, I did not find it correctly. It should actually be -2.5 plus -12.5. Divided by 2. And this average velocity is actually equal to 7.5, which then makes this change in position of 31.25 meters, and therefore they match. So anywhere I said 15, it actually should be 12.5, which I did a lot. Well, I would definitely give myself a proficient there. We all make mistakes, it's okay. All right. So when finding the change in position, we can either use average velocity or area. I am usually going to use area just because that's what I was taught and that's what I've kind of always used. But if average velocity makes more sense to you, you are more than welcome to do that. But that is how we find all of the different things for position and velocity. Now you might be feeling overwhelmed. How am I going to keep this all straight? I am going to show you a trick. So I say that in physics, all graphs should be TSA approved. So T stands for title, right? In general, y-axis versus x-axis. So for a position versus time graph, that would be position versus time. S stands for slope, meaning what could the slope represent? In general, slope is found by doing change in y over change in x. So for this position versus time graph, change in position over change in time, which rings a bell to me as velocity. And if I forgot, I could look at the units and I can say, oh, well, I know x is measured in meters and time is measured in seconds, and oh, those are the units for velocity. And I can do A. A stands for area, which in general is a y-axis times an x-axis. So here, change in x times a change in time. That equation doesn't remind me anything. The units would be a meter times a second, and that doesn't remind me anything. So that tells me the area here means nothing. I can do the same thing for a velocity versus time graph. T. All right. Title is velocity versus time. S is change in velocity over a change in time, right, with units of meters per second over second, meters per second squared. So either from the equation or from the units, I know that that has to be acceleration. An area is a change in velocity times a time, or a meter per second times a second, which is a meter. So I know either from the equation or from the units that my area is a change in position. So if remembering all of this stuff felt overwhelming, if you can just remember how to TSA a graph, you actually don't need to memorize all of this stuff. You just need to remember how to use TSA. Okay? And that's it.